So even though we're going to do 9.5a tomorrow, Thursday on block day, 9.5 will not be a part of our quiz. Today's lesson is where the quiz is going to end. And so the review assignment that I want you to do Thursday night will be on anything 9.1 and 9.4 that we've covered so far. Okay? So today we just really want to wrap up the importance of having a good concept of convergence, having a good understanding of what it means to converge absolutely versus converging conditionally. And then we're going to start to dabble in talking about endpoints. We have not talked about endpoints for very many of our inequalities yet. Our inequalities have all been open for the most part. When we get to, so that is the next hurdle we have to get over. So we're laying the groundwork for 9.5. So just to review where we've come from yesterday, we've talked about the ratio test, and the biggest problem with the ratio test is that it only works if you have positive terms. And so then if you don't have positive terms, so if our thing comes out to be L of x, so if it's some kind of function expression, then we have to keep that absolute value. So it'll converge absolutely if L of x is guaranteed to be less than 1. It will diverge if L of x is greater than 1. And then if we have the equality of L of x being equal to 1, that's an inconclusive result. So you may have multiple choices that are going to get to the difference between does this converge or does it converge absolutely. And so you need to be able to say, okay, I needed an absolute value on that one, so then I have to say it's going to converge absolutely. When we use the word absolutely in English, it's a word of strength. Absolutely, 100%, I'm down. It's a very strong word. In math, it's not. It's a weak word. When you say absolute convergence, it is a weaker kind of convergence than plain convergence. And so if you can prove the weaker of the two, then the stronger comes automatically. But if you prove the stronger, the weaker doesn't always come. It's an if-then statement. So think about when you did Venn diagrams, maybe in elementary school, the set of things that converge absolutely, things that need the absolute value, is a lot smaller than the ones that are regular convergence. So one is within the other. The set of things that need absolute values is within the thing that needs regular convergence. So if you show something converges with absolute value signs, then it also is within regular convergence. It will converge for sure. But if you prove convergence without absolute value signs, you're not guaranteed absolute because it's a smaller subset. You may have picked one that's outside of that. So be careful of the converse. If it converges absolutely, it must also converge in a regular sense. But if it converges in a regular sense, it doesn't necessarily converge absolutely. They are not, the converse is not true. So that's our kind of your walk-away theorem in the yellow. If something converges by using absolute values, then we have convergence. But the reverse is not true. So if you're trying to say, if this converges, then there is no guarantee about the convergence with absolute value signs, which is the opposite of what we kind of think. We sort of think it should go the other way because the way we're used to using the word absolutely. But when we talk about absolute in terms of series, you're going to have to keep straight which one is the more powerful one. All right, so let's take a look at this. Use absolute convergence for this. So show, if you can show it with absolute, you've showed it for all, because you're showing it for a smaller subset, which would have to apply to the larger subset. All right, this is not geometric, so we apply our ratio test to the limit of n approaching infinity. So we'll apply our ratio test, so we'll have the sine of x to the n plus 1 power over n plus 1, and then multiplied by n over the sine of x. And you should be able to fly through the reducing of this pretty quickly at this point. We're going to get down to n over n plus 1 grouped over the sine of x to the n plus 1 over the sine of x to the n. So as we reduce here, the n over the n plus 1 term has a limit value of 1 according to L'Hopital. And then we are left with a limit function value of sine of x. All right, so we take that sine of x and we think about, all right, with the absolute values, is that a true statement? And this is just like what Juliet was asking about earlier. Sine of, yeah.
Sorry, what happened with the n over n plus 1?
L'Hopital, it was infinity over infinity.
Oh.
And so then I did L'Hopital in my head, and I got 1 over 1. So, sorry, I kind of did that fast. So this is what Rain was talking about. What Juliet was talking about, that the sine of x as a property is going to oscillate. Whoa, that was poor. Now, for most of the time, that will be less than 1. But what happens every once in a while? It equals 1, right? How often? Every time I get to here, it's going to equal 1. And here, and here, and here. Okay? And then what about the minimums? They're -1, but because we're in absolute values, that's also going to... So all of these are problematic as well. So it's fine as long as I'm not hitting one of those spots. So can you generalize how often it's going to hit one of those spots? Okay, the first time, like if we start, the first time, where's it going to hit it? Pi over 2. Not at pi, but pi over 2. Okay, and then when I get down to the lower one, that's 3 pi over 2, and then 5 pi over 2, and 7 pi over 2. So how do we write that in general terms? K pi over 2, but k has to be a specific, k has to be odd. Yep. So converges absolutely for all x not equal to k pi over 2, k is odd. So it will converge absolutely with that as our caveat. Now, we're going to deal with the equal to part that is coming. We're one lesson away for what to do with all those equality things. Okay, so since it's converging absolutely on that, we can say it converges. That's our conclusion.
You can say that, but just like we have to clarify only for that interval.
Mm-hmm. All right, so our ratio test has a couple different limitations. The limitations are the positivity, which then we have to switch over and use absolute values. And then there are some other limitations. We also talked about the big limitation if L of x is equal to 1. Okay, but I want to talk about some other special cases. I don't know, they're not limitations, and it goes to what Alex's question was today about number 17. Okay. If L of x equals infinity, or if L of x equals 0. Okay, so these are special cases on the ratio test. Now, when we already know that if L of x is greater than 1, it will diverge. So what Alex's question got to today, the series will diverge, and then you say with a radius, of 0. So if the limit function turns out to be infinity, we have a divergent series, and we say that its radius is 0. The radius of being 0 means that the interval doesn't exist because there is no convergence. That's why we say the radius is 0. On the flip side, if L of x does equal 0, it falls into the category of the absolute value being less than 1. So then we say that the series converges, and it converges with a radius of, what do you think? Of infinity, exactly. Which means it includes all values in the radius of convergence. The radius of convergence is so large it includes everything. So these are two special cases that they just want like a little bit of extra explanation, that yes, it falls into either the divergent half of the numbers or the convergent half of the numbers, but then we specify that it has a radius of 0 or a radius of infinity. All right, so this is summarizing that. If L is 0, the radius is infinity, and it converges everywhere. If L is infinity, then the radius is 0, and this series will diverge everywhere except at the center is the only place that you would have convergence, that only one little spot. There is no interval, okay? Only a spot of convergence. Okay, so let's take a look at this one. We want to investigate the convergence of this series, and we'll use the ratio test, and this is going to be an example of the special case. So we'll take the limit, and we'll look at applying the ratio test because it's not geometric. So we'll have n plus 1 as a factorial times x to the n plus 1. And then I get to divide right away by n as a factorial and x to the n. So the ratio of the n plus 1 term to the ratio of the nth term. Okay, Juliet, you want to try and reduce the factorial parts of it?
So you would pull out n plus 1.
Mm-hmm. And that's all you're left with, right? N plus 1 is it. That's the only difference between those two. Okay, the top factorial is longer by 1 term, and the only term it's longer by is n plus 1. Otherwise, all of it reduces. Okay, and then I'm also left, Alex, can you reduce the x term? Just x. Okay. All right. So then if we plug infinity into this, we get infinity plus 1 times x, which of course is going to be infinity. Okay. All right, so Kaylin, what's our conclusion? Since L of x equals infinity, okay, then?
It will diverge.
Okay, and what else?
And the radius will be 0.
Yep. Except at the center, x equals, and what is the center?
1.
Not quite. Nope. would only be 1 or negative 1 if we had an x plus 1 or an x minus 1 in our equation. Yep, it's 0. Okay, so in order to have a center, remember the center is x minus a to the n. And so if that's not present, then the center is 0. So 0 is the only place that this would converge. All right, so the last thing we've got to do is this inconclusive part. Okay, what are we going to do with that problem? So your Google Sheet that has all of your different tests on it has lots more spaces. And so we have more tests that will help us cover being inconclusive. Okay, well then we'll move on to a different tool in our toolkit, and we'll cover that starting on Thursday with the 9-5. Okay, so that's the final thing. We just need more convergence tests. Okay, when we're dealing with open intervals, we're fine, but we need to be able to figure out what's going to happen at our endpoints. Okay, so stay tuned for that.